Welcome to my Switching, Routing, and Wireless Essentials course. This should be the CCNA version 7 curriculum. This is the second of 3 courses. Moving on, let's talk about static and dynamic routing. This is the last section in this video, but this is actually one of the more important ones. So again, static and dynamic routing are not mutually exclusive. It's not one or the other. You can do both. So a static route are commonly used for the following scenarios. Basically, a default route to the ISP for routes outside the routing domain that are not learned through some form of dynamic routing protocol. When you want to specifically or explicitly define the appropriate path to flow through a network. And there are some times where you want data to flow a very specific path for security reasons, or because you are connecting to a stub network that you want to control traffic to and from. Static routes are useful for small networks, but as the network grows, the configuration of static routes becomes a little rougher. Dynamic routing protocols are implemented in any type of network consisting of more than a few routers. Basically, the routers will share information dynamically and they will update one another. So scalability are there. Routing updates are automatically and learned with one another. Basically, the overall routing topology of a network can be automatically updated when you're using dynamic routing protocols, which means it's scalable, it's growable, it's easier to maintain. So dynamic routing protocols are commonly used in a few different scenarios. Again, the larger networks, when there could be multiple changes, and for scalability. If we are comparing and contrasting the two, dynamic routing is independent of network size. Static routes will increase the complexity of configuration the larger network grows. The topology changes. Dynamic routing is automatic. Static routes, you have to have the admin make changes. Scalability is way easier on dynamic routing protocols, and it doesn't really scale well with static routes. Security, dynamic routes, you need to configure it, whereas static routes, the security is built in. So static routes are typically classified as more secure. Resource usage. Dynamic routes have to process these updates and these changes and whatnot, so they use more resources. Where with dynamic routing, those resources means higher level router, more memory, more processor. With a static route, no processing is needed. Path predictability. Dynamic routes will be path independent, where with static routes, the paths are explicit. So there are pros and cons for both. It just kind of depends on what you're trying to accomplish. We have a few routing protocols based off of our timeline. We're talking things like EIGRP, RIP version 1, OSPF. The most common OSPF that we're going to be using is going to be OSPF v3. That's going to be created early 2000s. We have things like BGP or RIP v2. All of the main routing protocols were developed in the 90s. Even though it's 2020 and beyond, we still are using routing protocols from 20 plus years ago. So the most important question that I get asked the most is, what are the routing protocols and how are they broken up? So we have two types of routing protocols. We have interior gateway protocols, IGPs, and we have exterior gateway protocols, EGPs. Basically, if we're talking who is going to manage it, it will be internal. If we're talking an external entity managing things, it will be an external or EGP. The internet is ran off of EGPs because, again, the internet is multiple ISPs that have to interconnect with one another. So an ISP might have their own IGP running that ISP collectively, but combining all of the IGPs will be a EGP. So I'm going to start with EGP because it's kind of the easiest. For IPv4, BGP is the main routing protocol that runs the internet. BGP is a exterior gateway protocol typically. I say typically because BGP can also be an interior gateway protocol, but that's part of the Cisco CCNP track and outside the scope of this exam. So we have our IGPs left. IGPs are broken down further into two main groups, distance vector and link state. The main takeaways from distance vector is distance vector will send the entire table to its neighbor, where link state will only send the updated changes or the link information to its neighbors. So distance vector kind of sends more details than it needs to, where link state only sends the information that it needs to send. Distance vector is slowly going away, and link state is kind of taking over. You'll notice in the next course, we're going to be focusing on link state routing protocol, OSPF, because that is what's kind of making a break for the dominance in our IGPs. So moving on, a routing protocol is a set of processes, algorithms, messages. Basically, it is the standard or structure that will be used to exchange route information. How to Route 1 and Route 2 exchange information. The routing protocol will define the rules that will be used to exchange that information. How do we discover remote networks? How do we discover when there's a change? How do we discover when to update one another? How do we choose the best path? Things of that nature will be defined by that routing protocol. The main components of a dynamic routing protocol are going to be the overall data structure, basically how the routing protocol will typically use tables and databases for their operations, and how it's stored in memory. The routing protocol messages, these are going to be the messages sent to and from, and the message types will be varying types of messages that could be used to discover things like neighbor routes, how to exchange information, how often should we check to make sure a route is up and alive, maintenance, and so forth. The last main component is the algorithm. The algorithm is a finite list of steps used to accomplish the tasks. And each message is basically will fill one of those tasks. How do I discover my neighbor? The algorithm will define how to do that and will define what messages to send and or receive to verify that information is accurate. The routing protocols will determine the appropriate best path route for each network. The route is then offered to the routing table. The routing table will accept the route and install it in the routing table for X amount of time. Again, lower the AD, the better. If there are multiple paths, the lower AD will always take precedent. And again, we already looked at the AD table, directly connected routes, static routes, and then the appropriate dynamic routes. Know the numbers. Best path is really depending on what protocol we are using. If we are using RIP, RIP uses the metric of hop count. If we are using EIGRP, this will be based off of metric bandwidth and delay values. Basically, it will look at the cost of communication and it will try to send it through the paths that have the most bandwidth, the lowest delay, and are considered the most reliable. OSPF will use a metric of cost. This will be a cumulative bandwidth from source to destination. If I go from A to C, it will actually calculate the paths and the paths costs using the entire network to determine which path will be the most efficient path. So again, metric is going to be the important key word here. Each routing protocol may have a different metric or way of measuring which will be defined as the best path. And you do need to know what metric these three use it. So RIP will use hop count, OSPF will use total bandwidth, source to destination, EIGRP will be based on the slowest bandwidth and delay values, and it may include things like load and reliability. Moving on will be load balancing. So EIGRP is one of the only routing protocols that does support unequal cost load balancing, where the rest of the routing protocols, they need to have equal cost. Basically, if I have two WAN connections and they're both gigabits, how do I send data out of them? And if they are equal, we can load balance the egress out of both of them. If they are not equal, we have to use EIGRP. Typically, you're not going to find a router with two asymmetric or two symmetric exit points. You'll typically find a router with a primary internet connective interface and a backup internet connective interface, and they will be different speeds. Because again, why would you pay for two active connections of the same speed if one is just more of a backup? Questions, concerns, please reach out. Thank you.